So we looked at the number of permutations of n objects taken all at a time was n factorial. So let's look at a few more examples doing this. Example 1 says, how many permutations are there of the letters of the word Regina? There are 6 letters there. And if you're arranging all of them, they could be arranged in 6 factorial ways, right? Using the fundamental counting principle, you could mark down 6 spaces. There'd be 6 choices for the first letter, and then 5, and then 4. Again, you have to assume that it's like Scrabble tiles. Like once you use a letter, it can't be used again. And we saw that the factorial key, or the factorial function, can be found by going math over to probability, and number 4 in that list is factorial. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. This just saves you typing all those numbers in. And we get an answer of 720. The word Kelowna, there are 7 letters there, so that could be 7 factorial, which you could put in your calculator. Or if you wanted to, because we have 6 factorial in our calculator already, 7 factorial is the same as 7 times 6 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. If you put a 7 in front of that and go 7 times all of that, that's the same as 7 factorial. 7 factorial is the same thing as 7 times 6 factorial, so we can just go times 7, our previous answer, and get 5,040, which is the same answer you would get if you just did 7 factorial. And how many ways can 8 children line up at a water fountain? Well, that would be 8 factorial, or 8 times 7 factorial, because I already have 7 factorial in my calculator. I can just multiply that by 8. But just to be sure, if you go 8 factorial, you'll see you'll get exactly the same thing, 40,320. Okay, we saw yesterday that we're not always arranging entire sets of objects. If there are 7 members on the student council, how many ways can the council select 3 students to be chair, secretary, and treasurer of the council? So this can be done using fundamental counting principle. Mark down 3 spaces because you're selecting 3 students. There'd be 7 choices for the first position, then 6, then 5. Right, so you could do it that way. 7 times 6 times 5 will give you 210. It can also be done using factorial notation. 7 times 6 times 5 can be found by going 7 factorial over 4 factorial. And this work here just shows that that does give you 7 times 6 times 5, because 7 factorial can be written as 7 times 6 times 5, and then we'd stop at the 4 in that expansion, put a factorial on the end because there's a 4 factorial on the bottom, and they cancel. And we did some of this yesterday. So this process just shows that 7 times 6 times 5 can be found by going 7 factorial over 4 factorial. The notation NPR is used to represent the number of permutations or arrangements in a definite order of R items taken from a set of N distinct items. A formula for NPR is N factorial over N minus R factorial. And that is on the formula sheet. So you don't have to memorize it. But we can also do it on the calculator. NPR can be found by doing those following keystrokes. You put the N value in first, and then you go same place that we found our factorial function, math over to probability, and you see number 2 in the list is NPR. So if we look at the situation that we have above here, you have 7 members, you're going to choose 3, and order matters. So that would be 7P3. Using the formula, it's N factorial over N minus R factorial, or 7 factorial over 4 factorial. So that's the expression that we have here over on the left. And we know that will equal 210. We did it by simplifying. We can also do it using factorial in our calculator. So if I go 7, math over to probability, choose number 4 for factorial, divide it by 4, math over to probability, choose my factorial, you get your answer of 710. So that's using the formula and factorials. You can also doing it using 7p3 in your calculator. You have to put the 7 in first, go to math, over to probability. Number 2 in the list is NPR. So that gives us 7p. You put the 3 in, hit enter, get the same answer. So it does that calculation for you. It applies the formula for NPR. Okay? If we replace the R by n in the above formula, we get the number of permutations of n objects taken n at a time. So this is where you're arranging all of the objects, and so that is, as we know, it's n factorial. If you use the NPR formula and do NPN, which we know is n factorial, using the formula, it's n, the first number, factorial, over the difference between the two numbers, n minus r factorial. So this gives us n minus n factorial o, or n factorial over 0 factorial. We already know that NPN is arranging all the objects, that's n factorial. So n factorial is equal to n factorial over 0 factorial, which means that 0 factorial has to equal 1. We talked about this yesterday, now we see why. This is the reason that 0 factorial equals 1. That's probably not going to come up again. Anything talking about 0 factorial, probably not going to come up again. But again, we talked about this yesterday, the fact that 0 factorial has a value of 1, and you should get that if you go 0 factorial in your calculator as well. And you do. Okay, so you don't even need to understand why that is true, but this relationship that we just went through is a proof of why it's true. In a South American country, vehicle license plates consist of any 2 different letters, which means no repetition, followed by 4 different digits. Again, different means no repetition. Find how many different license plates are possible by first, the fundamental counting principle. So you'd have to do this in 2 steps. The first step is your letters, and so times your 4 digits. So 2 different letters. There are 26 letters in the alphabet. So you would have 26 choices for the first, and because they have to be different, again, that means no repetition, there'd be 25 choices for the second. And then followed by 4 different digits. There are 10 digits to choose from for the first. Again, different means no repetition. So using the fundamental counting principle, that's what this will look like. We'll have 26 times 25 as our first part. That's 650 times 10 times 9 times 8 times 7. 5,040. And then those are multiplied together to get our final answer. 3,276,000. Using the fundamental counting principle. But this can also be done using permutations. Again, you'll have to do the 2 different parts. The first part is choosing 2 letters from 26. That'll be 26p2. Times, then you're choosing 4 digits from 10. And order matters, so that's why we're using permutations. So it'll be 26p2 which gives us the 650 times 10p4 which gives you the same 5,040. So that'll give us the same answer. Now you could have put this entire expression in and do it all in one step. 26 P2, just have to use the arrow key to go over away from the 26. Whoops, I chose C. I need to fix that. So there's the 26P2 times 10P4. So it'll do it, find the value of each and multiply them together. So again, what this also shows us is that when you use the fundamental counting principle, you're using permutations, okay, where order matters. Again, we're going to get into next week, we'll be talking about combinations where order doesn't matter. You cannot use the fundamental counting principle for combinations. Only for permutations. It means order matters. Okay, how many different arrangements are there using all the letters of the word formula? Well, there are 7 letters there, so it'd be 7 factorial. Or you could go 7p7. That's the same thing. Doesn't matter. You can either go 7 factorial, which is 5,040, or you can go 7p7. It's the same thing. 5,040. Right, so either way, it's 5,040. How many different 3-letter arrangements are there? So now that'll be 7p3. That's a simple way to do it. You could also use fundamental counting principle. Mark down 3 spaces. There'll be 7 choices for the first letter, then 6, then 5. Multiply those together. 7 times 6 times 5 is one way to do it, or going 7p3. Same thing. 210. Number 5 says evaluate that using the formula. So 9p4, and again, this formula is on the formula sheet. It's n factorial over n minus r factorial. 9 factorial over 5 factorial. Nine factorial over 5 factorial is 3,024. And just as a check, you can go 9p4. Get exactly the same answer. Okay, so they both work. Number 6 says show that 100 factorial plus 99 factorial is the same as 101 times 99 factorial. We want to show that these two things are equal, that they have the same value. So you're either going to work down the left side to get the right side or vice versa. It doesn't really matter which way you do it, but I'm going to work down the left side. I'm going to say that 100 factorial is the same thing as 100 times, and we've done this before, where you can expand it by using a series of factors. Whatever factor we end with, we put a factorial on the end, and I'm actually going to end at the next factor of 99 and put the factorial on the end of that, because now I have a binomial, and each of those terms has a factor of 99 factorial in it. Right? This is your first term. This is your second term. They both have a factor of 99 factorial in there. I can take that out as a common factor. A common factor of that expression is 99 factorial. To get the other factor, to get what's inside the brackets, you divide each of those terms by the common factor of 99 factorial. When you divide this first term by 99 factorial, they cancel. You're left with 100 plus. When you divide the second term by 99 factorial, you're dividing something by itself, you'll get 1. And 100 plus 1 is 101. So it's the same as what the right side is. So we've shown that those two expressions are the same. Right, number 7. There's been questions like this, similar to these on the diploma exam, only they will use the directing word determine, or algebraically determine, or algebraically solve the equations. This means you have to show your work, because you can definitely do guess and check. You want to find the value of n such that np2 is 20, so we might try 4p2. Too small, let's try 5p2. There we go. We know that our answer needs to be 5, just by guess and check. However, we need to determine it algebraically, so we will use the NPR formula. And then, like we did yesterday, we can simplify the expression on the left by expanding either the top or the bottom. Remember, you always expand the larger of the two expressions, which would be n. N is bigger than n minus 2. So n factorial will be n. The next factor in the expansion will be 1 less, n minus 1. The next one would be n minus 2, which is where we'll stop and put a factorial on the end, because that's our denominator. They will cancel now. The n minus 2 factorials will cancel. So you'll have n times n minus 1, n squared minus n. I'll bring the 20 over to make my quadratic equal to 0, which we always do, so we can factor. We can solve by factoring. The factors there will be n minus 5, n plus 4. So according to this equation, my answers for n would be 5 and negative 4. But remember, n refers to a number of items you're choosing from. It can't be negative. So that is an extraneous answer. The only one that works is 5, which we already know to be true. We did it by guess and check to see that our answer would be 5. Now we see where it comes from algebraically. All right. For question B, I would start this one by dividing both sides by 2. So now we want to know where NPR equals 60. So using the NPR formula, it's n factorial over n minus r factorial. So the top, on the left, we will expand. So that we get it to n minus 3 factorial, or a factor of n minus 3 factorial on top, so that they can cancel. And now we're going to have a third degree polynomial. So let's first multiply the n minus 1 and the n minus 2 together. That'll give me n squared minus 3n plus 2. Multiply out the n now. And bring the 60 over. And there's the third degree polynomial that we need to solve. And we factored these. Back in chapter 3, we factored third-degree polynomials. We used our graphing calculator to help us find the first x-intercept, then we used synthetic division to get the quadratic factor. So we'll go to y equals, we'll put this equation in there. Zoom 6 to set our windows to their standard settings. So in that window, it only looks like we have one x-intercept. It looks to be at positive 5. Let's go trace 5, enter. Yep, positive 5 is an x-intercept. So x minus 5 would be a factor. We would change it to x plus 5 so that we can add as we're going along with synthetic division. That's what we did. 1 times 5 is plus 5, and we add. 2 times 5 is plus 10, and we add. 5 times 12 is plus 60. We add and get the remainder 0 that we knew we needed to get. We knew that x minus 5 was a factor, which means it divides evenly into the polynomial. But what this gives us, it gives us the other factor. So again, n minus 5 is one factor. The other factor is n squared plus 2n plus 12, which cannot be factored. So what that means is that if there was a 0 for this, it would be irrational. We'd use the quadratic formula to get it. But remember, we said at the start that n had to belong to the set of natural numbers, because n is the number of items you're choosing from. It has to be a natural number. So therefore, there's only one answer, and that's n equals 5. So this is, we'll say, irrational, or it actually could be imaginary too. If the discriminant, remember, is negative, that means there are no solutions to that quadratic. You wouldn't know which of those two it is until you use the quadratic formula, but we don't need to. Because if you use the quadratic formula and you do get answers, they will be irrational, because that cannot be factored. So the only answer that will work would be n equals 5, which we can check. Two times 5p3 does equal 120. So it works. And it works. Okay? So for practice, you should work on page 524, 525, questions 1, 2, 4, 6, and 7. I will post these solutions to Google Classroom so that you can check your answers. Again, I encourage you to do the practice. It's going to help you when it comes time for the quiz and the test.